This is Mr. Craig, and I want to discuss electrochemistry. I believe this is our first lecture dealing with electrochemistry, and a lot of this is going to have some review. The first thing I want to talk about is the review of oxidation and reduction. Do make sure that you know what is happening when something is oxidized and when something is reduced. Do realize that we did talk about this earlier in the year, that when something's being oxidized, then it has a loss of electrons. If something is being reduced, then it's gaining electrons. Also, be sure that you know the oxidation state or the oxidation number for an atom when it becomes part of a compound. Do remember that metals want to have a positive charge, where non-metals want to have a negative charge. And we should be able to identify what the common charge is for an ion. Now, when we look at a periodic table, again, just like with your periodic table, it's not the same as the one that I have here, but you'll notice that there's no markings on the top here, where we don't have any like group 1A, 2A, and 3A, and so forth and so on. What we do care about is knowing what the charge for a potential element is based on if it's a metal or a non-metal and how far away from the noble gases that element actually lies. So when we look at, say, the noble gases, the far column over here on the right, that's what the common charge deals with. So if I'm looking at, say, magnesium, element number 12, and I want to say, okay, well, what's the common charge for magnesium? Well, is it easier to gain 6 electrons, or is it easier to lose 2 electrons? Well, for magnesium and everything in that column, or in group column 2, or the alkali earth metals, it is much easier to lose 2 electrons, therefore magnesium will have a +2 charge. Actually, everything in group 1A wants to have a +1 charge, everything in group 2A wants to have a +3, everything in group 3A wants to have a, everything in group 3A wants to have a +3. Then when we get over to the column here with the carbon, then it gets a little muddy. Those elements want to have either a +4 or a -4 charge, but there's also some other charges that are involved there. So group 4A, you're not going to be held responsible for knowing the common charge. But once we jump over the nitrogen, everything in that column, that is a non-metal, will have a -3 charge, oxygen -2, fluorine -1. So again, it's all about how far away from the noble gases are these elements and the common charge. So you should not have to have those charges on your periodic table to determine what the charge is. Now, when we look at the transition metals, again, the transition metals are our d orbital elements, okay, down here in the d block. Come back here. When we look at the d orbital electrons, the d orbital elements, you don't have to know what the charge is. In other words, you don't have to memorize that. Oh yeah, lead over here, not necessarily a d orbital element, but it has either a +2 or +4 charge. That's a multiple charge metal. You don't have to know that iron has a +1 or a +2. However, you should be able to determine what the charge on the metal is based on the charge of the non-metal. So making sure that you know your 10 polyatomics, and I'll talk about that here very shortly, making sure that you know the common charge for a single non-metal element, and being able to do the algebraic sum to determine what that charge is. Now, don't forget about the aluminum, zinc, silver slide, or I call it the aluminum slide. You must know the charge on zinc. You must know the charge on silver. Get off of there. So remember that aluminum's 3, zinc is +2, silver is +1. So that's the aluminum slide, 3, 2, 1. All the others have multiple charges that we care about. All right, getting back to the notes here. Again, so know your common charge. You'll never need to memorize the possible charges on the transition metals. I'm looking right here. But you should be able to determine the charge or the oxidation number based on the non-metal. All right. Be sure that you know your 10 polyatomics. Again, the 10 polyatomics. And I know some of you, I haven't remembered that in a while. Remember them. You need to know these 10 polyatomics. Also, make sure that you know if I gain an oxygen or lose an oxygen or lose 2 oxygens, how to name those polyatomics. Very important, guys, now that we're getting close to the AP exam. Let's see here. Oxidation reactions are also known as redox reactions. We did this very, very early on in the year. If you don't remember how to do a redox reaction, be sure that you go back and review that. You will see that on the multiple choice portion of the AP exam. However, what we're doing today is, quote unquote, very simple redox. In other words, I want to find out when we look at a reaction here, what's going on, and I know it says a very common redox example or a demo, and I'll show that when I get back, is where we take an iron nail and we put it in a solution of, in this case, copper sulfate, copper 2 sulfate. And what's happening is that the iron metal is actually replacing the copper in the solution, and we actually see the formation of solid copper on this iron nail. You'll see that when we get back here. And then the iron that was once a solid now becomes aqueous, and it changes the color of the solution from this beautiful aqua blue to kind of a dark grungy color. So it's not a very pretty reaction, but we do have a single replacement. And when we talk about a redox reaction, it is a single replacement reaction most often. And what's actually happening in this reaction? An oxidation reaction is taking place as well as a reduction reaction. The iron, which has no charge, is losing 2 electrons and becoming a +2 charge. However, the copper that has a +2 charge is gaining electrons. Notice that the electrons are on the same side as the ion itself, or on the left side. So it's gaining 2 electrons and becoming neutral. In other words, it's becoming more negative, even though the element itself is not negative. So when we talk about a reduction, we're talking about a gaining of electrons, where oxidation is a loss of electrons. And that's what this little saying here is. So when we talk about whether something's gaining or losing electrons, I like to use, Leo says GER, but you can also talk about oil rig. So oil rig. And if we talk about oil rig, it's oxidation is losing, where reduction is gaining. Not a big fan of oil rig, but hey, whatever works for you is fine by me. Oxidizing agents and reducing agents. Let's take a refresher on that. Remember, when we talk about agents, number one, they must be on the reactant side. Also, the agents do the opposite, or they have the opposite name of what they're doing. So in other words, the iron in our example here is being oxidized. Therefore, it's allowing the copper to be reduced. Therefore, the solid iron is our reducing agent because it is oxidized. When I look at the copper +2 metal, or whatever comes with the copper +2, the agent is the whole package. So if I told you that we had copper sulfate would be the agent. But what's happening is copper is being reduced and allowing iron metal to be oxidized. Therefore, the iron +2 is the oxidizing agent because it is reduced. So the agent allows the other thing to take place. All right. So again, that's where the agents are at. Let's see. Let's turn the page over to the back side here. Electrochemistry. That's what we're doing right now. It's the study of the interchange of chemical and electrical energy. And this is what we do for batteries, for other types of reactions that take place for single replacement reactions. It's an interchange of chemical and electrical energy, which is kind of cool. We're primarily concerned with 2 processes, oxidation and reduction reactions, and the generation of an electrical current from a spontaneous reaction. And the key here is, we've already talked about spontaneity. If the reaction takes place on its own, we don't have to do anything except place them in the substance that they're going to react within. This is a spontaneous action. And we'll talk about whether something is spontaneous or not here in a few minutes. All right, so reduction potentials. Finally, if you take your periodic table out, go ahead and take your periodic table out and take a look at it. Except I want you to flip the periodic table over and look at the back side. And you should see a table that looks something like this. It says standard reduction potentials in an aqueous solution at 25 degrees. Okay, that's what I want us to look at. This is the first time we've actually looked at this information. But these are standard reduction potentials. Notice that Everything on the left side is a reduction reaction, or it's being reduced. Okay. Back in the day, they used to have oxidation or standard oxidation potentials where they had the reactions flipped, and the whole table was inverted. So fluorine, which is on top here, is actually on the bottom on a reduction, but we don't need to worry about that. What I do want you to realize is the voltage, this column over on the right here, where it talks about the voltage here, and we have positive voltages up on top, and we have negative voltages near the bottom. And notice that lithium has a negative voltage when we talk about lithium ions going to lithium solid by gaining 1 electron. So that's going to have some significance here. And notice that we have nonmetals up here, actually the fluorine, the bromine, let's see, there should be another one up here. I thought chlorine, there's chlorine. Okay, so you have fluorine, chlorine, bromine, and iodine should be, there it is, iodine's down here. So we have our nonmetals that like to be oxidized. And there's a few other elements on here that, and you'll notice that they're ions that actually like to be reduced as well. So we'll come back to that table here in a moment. All right, so when we talk about reduction potentials, we looked at our sheet and we saw that for, I have my first example here where lithium, the lithium here has a reduction potential of a negative 3.05. However, if the lithium is being oxidized, which lithium loves to be oxidized, it has a voltage with a positive voltage. Now, you're going to find out real quickly here that reactions that are spontaneous want to have a positive voltage. In other words, they want to generate a voltage. And I would dare say that if we look at your cell phone battery, what kind of battery do you have? I'd be willing to bet that you have a lithium-ion battery. Because what happens, solid lithium, which we can package very easily, is able to change into lithium ions and give us a very high voltage. So when we look on our standard reduction potential sheet, that's why we use lithium batteries, because it's right down here. It gives us the most bang for our buck. Back in the day, they used to use nickel-cadmium. Nickel and cadmium are a little higher up, and we didn't have the technology to make better batteries as we do now. So that's why we use lithium. Okay, so we'll come back to that. Let's clear that off. Oops, clear everybody, guys. All right, so the standard reduction potential, if it's a reduction reaction, then we're going to use the values that are on the table. If it's an oxidation reaction, we simply flip the reaction and flip the sign. Nothing wrong with that. We can do that. All right. You can calculate the potential, and I'm right here. You can calculate the potential of a redox reaction if you know the potentials for the two half reactions that actually make it up. There are two important things to remember when calculating the potentials of a redox reaction. Add the potential for the oxidation half reaction to the potential of the reduction half reaction. And the most important line on here, number 2, we never ever multiply the reduction potentials. In other words, say that if I have lithium that we know has a +1 charge, and say that we're reacting that with aluminum that has a +3 charge, we know that we have to multiply the lithium by 3. We do not multiply the voltage by 3. We just simply add up the potentials, and if we get a positive voltage, this is going to happen. If we get a negative voltage, it is non-spontaneous. So again, simply add the potentials and then never ever multiply the potentials based on how many times we have to multiply it. So it's not like Hess's law where, okay, I have to multiply this equation by 3 to balance it out, therefore I'm going to multiply the delta H's. Not doing that with this. All right. Let's see here. Since iron is being oxidized, we find the reduction for the iron 2, and again, this information is on your chart. Since it looks like here, this is an oxidation, it'll have a positive voltage, and I'm looking at this example up here, I apologize. So this is our iron nail going to iron ions, and again, we don't have any oxidation reactions on our standard reduction potential sheet, so we have to flip the equation, therefore flipping the sign. We know that the copper +2 is being reduced. Luckily, it has a positive voltage. So when we add these two voltages together, we get a positive voltage. So did this reaction happen? Well, I plan on showing it to you when I get back. So the answer is yes. and it is spontaneous. So a positive voltage gives us a spontaneous reaction. Now, the equation that we're using to calculate this, again, going back to delta G, we talked about it in kinetics, is if delta G, the free energy, has a negative sign. Delta G is negative. If delta G is negative, this reaction is spontaneous. And again, spontaneous in the forward direction. So forward means, yes, we're taking reactants and forming products. So the only way that that's going to happen is if we have a positive voltage. If I have a negative voltage, then that negative sign actually changes that voltage into a positive value, which makes delta G positive. All right. Now, what are these other two values here? The N and the little funny looking F here. Okay. That's actually a sign for Faraday's constant. And Faraday's constant is on your equation sheet. Excuse me, and it's equal to 96,500 joule volts, or joules per volt. And that actually is equal to a coulomb per mole of electrons. We'll use that equation actually in the next set of examples when we do the math. The N represents how many electrons are actually exchanged. So if we have, say, in our example up here, we have 2 electrons here, and where's the other reaction? 2 electrons here. So we have an exchange of 2 total electrons. The copper absorbs 2 electrons while the iron is losing 2 electrons. So the example where I gave with the aluminum and the lithium, okay, my pen's not working very well, but aluminum would have a +3 charge, the lithium would have a +1 charge, so it would be a total exchange of 3 electrons when we do a calculation like that. Again, if delta E is negative, that means delta G will be positive. That means the reaction will not be spontaneous in the forward reaction. And if we have delta G that is negative because our voltage is positive, then we have a reaction that will be spontaneous. Example number 1, which of the following would be the best oxidizing agent? And from our choices we have chlorine, Cl2, iron metal, no charge, sodium, no charge, sodium ions with a +1 charge, and fluorine ions with a -1 charge. Now, the question also wants us to explain why this would be the best oxidizing agent. Now, hopefully we remember what oxidizing agents are or what they're doing. Now, if something is an oxidizing agent, it first must be reduced. So the thing that we want to look at is if it is a good thing that is being reduced, that means it's going to have a positive voltage when it is reduced. Now again, what does reduction mean? It means that it's gaining electrons. So when we talk about an oxidizing agent, we're talking about something that is allowing for another substance to be oxidized while it itself is being reduced. All right, so let's get right to it. Looking at the first example, if something is being reduced, like in our case here with chlorine, what that means is it's going to gain electrons, and since there's 2 Cl's, and we know that chlorine wants to gain electrons, we have to find out what its voltage is. So from our standard reduction potential sheet, we come over and we look for chlorine, which is right here. It's the 4th one. And when chlorine is reduced, changing from chlorine gas to chlorine ions, it has a positive 1.36 voltage. So we're actually starting off pretty well here. So we have a positive 1.36 voltage. Now the best oxidizing agent, or the best thing that's reduced, will have the highest voltage. All right, so let's take a look at the next example, iron. And again, this is solid iron. Now, does iron metal wish to be reduced? Now, ask yourself, what do metals want to do? Do they want to gain electrons, or do they wish to lose electrons? Well, if for some reason you're having a bad day and you can't remember, go to your standard reduction potential sheet and try to find iron that is a solid, and when it changes into a charge. So actually, that's iron +3, so let's go down a little bit further. Here's solid iron, And changing into that, the only thing that I can see here is that iron metal is formed by a reduction of ions. So when we look at iron metal wants to have a positive charge. And hopefully you recognize or remember from at least general chem or from writing balanced equations earlier on in the year that iron likes to have a +2 or a +3 charge. The only way that iron is going to get a positive charge is by losing electrons, not by gaining electrons. So iron metal is out. All right, so looking at the next example, sodium. Hopefully you've learned something from the last example here, that if we're looking at sodium, sodium too is a metal, and sodium itself, from our reduction, when it's reduced, the only thing that we can do with sodium is, if it's an ion, reduce it. So since sodium is a metal, and we all know that sodium wants to have a +1 charge, it too cannot be reduced. Therefore, it's not going to make a good reducing agent. Oxidizing agent. It'll make a great reducing agent, but it will not make a good oxidizing agent. All right, so let's take a look at sodium +1. So sodium +1, this is a good thing. Sodium +1 can be reduced to form solid sodium, but let's take a look at the charge. So we still have that highlighted, and when sodium ions are reduced to form solid sodium, we have a negative 2.71 voltage. Well, a negative voltage is not something that is favorable. Now, based on the previous video, we showed that equation where we had delta G was equal to negative N Faraday's constant times the voltage. If we have a negative voltage and we have a negative sign to start that off with, that's going to cause delta G to have a positive value. So for delta G to have a negative value, we have to have a positive voltage. So sodium ions are not a very good oxidizing agent because it produces a negative voltage. So we want to rule that out. All right, the last example, fluorine with a -1 charge. Okay, well, we have a nonmetal here. Can fluorine become more negative? Well, we know that fluorine wants to have a -1 charge, but we don't know, or we know for a fact, that fluorine never wants to be a -2 charge. Besides, there's no place to put that extra electron. It has 7 valence electrons. It wants one more. Taking on a second one just would not make sense. So when we look at fluorine, fluorine likes to be reduced, but since it's already a negative ion, it too will not be reduced any further to make a more negative charge. So there are two options here, the chlorine and the sodium +1, and we just ruled out the sodium +1 because it has a negative voltage. Therefore, the best oxidizing agent of these 5 would be chlorine, and that's actually chlorine gas. All right, example number 2. It says a piece of copper metal is placed into solutions containing each of the following 3 cations. Which ions will be reduced by the copper metal? So here's our scenario. We've got actually like 3 containers. Maybe this one has the 10+2. Here's another beaker that has zinc ions. And again, these are all solutions. Okay, and then we have a third beaker that has some silver ions in it. And when we look at that, what we're doing is we're placing copper metal in each of these. And the question's wanting to ask which of these will cause the reduction of the ion itself to form solid metal. So what we want to do here is we want to actually do the calculation to see if it is a spontaneous reaction. All right, so here's our diagram. Let's go ahead and get right to it. So we know that copper metal, again, since metal itself has no charge, and what's happening is it is being oxidized. We know that it's being oxidized because that's what metals wish to do. Now, we do have a dilemma here. Copper could be a +1 or a +2 charge, so we want to find the most favorable situation here. So when we come to our standard reduction potential sheet, we see that we have 2 coppers that are metals here. The copper plus 1 yields a positive voltage of 0.52 when it's reduced, and the copper plus 2 yields a positive 0.34 voltage when it's reduced. However, since we are oxidizing the copper, we want to go with the smaller value because it's a smaller negative value. So what's going to happen, nature will automatically make copper metal, when it is oxidized, a plus 2 charge because it yields a smaller negative voltage. Okay. Now, don't get excited that it has a negative voltage, because what we're looking at is the other thing, to make sure that if this is going to be a spontaneous reaction, that the total voltage of this reaction is positive. So looking at the first one, the 10 plus 2, well, let's go ahead and do that. We know that 10 would like to be reduced. We take it from an ion to a solid. So let's find out what that value is. So 10, let's find it, Sn plus 2 going to solid right here. So when the 10 is reduced, it gives a negative 0.14 voltage. So the 10 ions will not be reduced by the copper in this reaction because it will yield a negative value, actually a negative 48. Okay, so the 10 plus 2 will not be reduced when copper metal is placed into the solution. All right, let's look at the next example here. We already know we're going to go ahead and use the copper. I'm going to erase the 10. Okay, so ready? Erase that line too. All right, so let's look at the next example where we have zinc plus 2, and it will also be reduced to form solid zinc. So let's find out what that value is. Zinc. Where are you, zinc? And half of the fun with doing this is just being able to find these things. So here we go. Here's zinc that's being reduced. And when it's reduced, it also has a negative value. So a negative 0.76. So that too will not yield a favorable voltage. So when we look at that, 1. So a negative voltage there. So the zinc ions will not be reduced in this reaction either. Okay? And again, what we're trying to get is a positive voltage by all this. So hopefully in our last example here, using the silver, we'll get a favorable response here. So silver plus 1, when it's reduced, will form solid silver. And go to our standard reduction potential sheet. Silver's near the top. Here it is. Okay, so we get silver that has a 0.8, and that's a positive value for a reduction. So when we plug in the 0.8, and again, it doesn't have to be a large voltage, it just has to be positive. So when we take a look at this, we do have a positive voltage, which in this case I believe is 4.6 voltage. So to answer this question, the only thing that will be reduced by copper metal, and again, what's happening is the copper itself, metal, no charge, is turning into copper ions, and it's losing 2 electrons, and it's allowing the silver to gain those electrons. Now, this isn't a balanced equation. If we were to balance this, what we would need to do is multiply this by 2, stating that, okay, for this copper metal to lose 2 electrons and for the silver to gain those 2 electrons, we'd have to have twice as much copper. Now, here's a really very important point. What we don't want to do is, since we have a multiplier of 2 here, we do not multiply this by 2. We never ever do that. The reason why we don't do that is because as long as we have silver and as long as we have copper, the reaction's going. This is what's called an intensive property. Intensive properties don't care, or it doesn't matter how much of the material we actually have, just as long as we have it. Now, that's different from extensive properties. And I think I spoke about extensive and intensive properties earlier in the year. Here's an example of an extensive property. If I had a coffee cup amount of size of water and a swimming pool amount of water, which one would boil if I put a Bunsen burner under each one of those? Well, hopefully you'd say the coffee cup amount of water would boil first, because it has a smaller amount of water present. However, if I have that same coffee cup amount of water and that same amount of swimming pool water, and I ask you, okay, which one has a higher boiling point? Well, the boiling point's the same. That's an intensive property. As long as we have pure water, its boiling point will be the same, regardless of how much we have. So when we talk about intensive and extensive properties, voltage deals with an intensive property. As long as we have some silver and as long as we have some copper and this reaction's going forward, it doesn't matter how much silver we have. So if I need to have a multiplier of, say, 5 or 10 or whatever to balance this out, it doesn't matter, just as long as I have silver. So that's, by definition, an intensive property. That's why we would not multiply the amount of material that we have by the voltage. The voltage is set. Do not multiply it. All right. Let's look at the next example. Example number 3, it says, is the reaction spontaneous or non-spontaneous, and explain why, and then show all your work. All right, so we're looking at a single replacement reaction here, and the question's asking, will the lithium replace the copper in this reaction? So what we'll have is, we'll have lithium metal plus copper chloride, and if the lithium is capable of kicking the copper out, then we'll form lithium chloride. Now again, lithium has a +1, chlorine -1, and forming copper metal. So what we need to do is, first thing, let's find out the charges for each of these. Well, lithium by itself has no charge. Copper in this example has a +2 charge when it's hooked up with the chlorine, and the copper over here has no charge. So let's do the half reactions and do a voltage calculation. So let's start off with the lithium. Lithium, no charge, going to lithium +1 and losing 1 electron. Go to your standard reduction potential sheet, and lithium is near the bottom here. So lithium, when it is reduced, has a -3.05 voltage. However, lithium is oxidized in this example, so we're going to use the 3.05, but as a positive value. So we have a positive 3.05 voltage, starting off well there. And then let's take a look at the copper, +2, going to solid copper. So we know that we have to gain 2 electrons for it to become neutral. So let's go ahead and look at our sheet again. I think we've used this in the last example. Copper, here we go. When copper +2 is changed into solid copper, it has a positive voltage of 0.34. So when it's reduced, and that's what's happening, a positive 0.34. So this is definitely going to happen. So we have a positive 39 voltage. So yes, this reaction most definitely will occur. Okay, now again, notice that we have 2 electrons here and just 1 here. The reason why I didn't balance the equation up here is because I want this to balance it for us. Notice that there's 1 chlorine over here and there's 2 over here, so I need to put a 2 there and a 2 there to balance out. And again, the half reactions do that for us. So if you forget to do that, that's okay. The half reactions should help us out in that regard. All right, let's look at part B. We have chlorine that's reacting with sodium fluoride. So let's go ahead and write that out. Chlorine plus sodium fluoride. Now, ask yourself this. Who is the chlorine trying to replace? Is it trying to replace the sodium, or is it trying to replace the fluorine? Chlorine is a non-metal. Chlorine will not ever replace a metal. So chlorine is trying to replace the fluorine here. Remember, in a single replacement reaction, the thing that stands by itself, whether it's a metal or a non-metal, will replace its own kind within the compound. So up above here, we had a metal, lithium, is going to replace the copper. We would not try to replace the chlorine in this case. Not going to happen. Okay. So what we want to, if we do, or if the chlorine is able to replace the fluorine, we would have sodium chloride, and we would form fluorine gas. Okay, and again, it's not balanced, but we'll go ahead and work from there. All right, so let's start off with the 1/2 reaction. Let's see what's going on there. So Cl2 going to chlorine ions. Since we have 2 there, that means we have to have 2 chlorines here. And again, be charge savvy, so make sure you have your charges on there. Since there's 2 chlorines and it goes from no charge to a -1, that means it's going to be reduced. So we want to look on our standard reduction potential sheet. Chlorine's the 4th one up there, and again, it has a voltage of 1.36. So that's starting off well. We have a positive 1.36 voltage. Okay, so now let's look at the fluorine. So the fluorine goes to fluorine negative goes to fluorine gas. Well, we need 2 of those. And if it has a negative charge, then that means that the fluorine is oxidized. Well, that can take place, but the question is, will that take place? So the very top here, we have fluorine gas that's reduced to make fluorine ions, and it has a positive 2.87 voltage as it's reduced. However, in our reaction, it is oxidized, so that means it has a negative 2.87 voltage, which means that this reaction has a negative voltage. So this one will not take place. No reaction. Okay. All right. Again, positive voltage means that it will be spontaneous. A negative voltage means that we have a positive delta G, which is not good. All right. Part C. Magnesium reacting with silver bromide. So we have magnesium, no charge, silver bromide. And again, what's going to try to happen is the magnesium is going to try to replace who? The silver or the bromine? Well, magnesium is a metal, so it will try to replace the metal in this reaction. So it'll try to kick the silver out. So we form magnesium bromide. And again, magnesium has a +2 charge, so we need 2 bromines. And try to form pure silver. So if we have 2 over there, then that means we need 2 there. Okay, so let's find out if this will take place. So starting off with our first reaction, magnesium has no charge where it has a +2. Silver has a +1 where it has no charge over here. Alright, so magnesium no charge going to magnesium +2. How does it do that? Well, it loses 2 electrons, so it is oxidized. So let's get a value for that. Magnesium. There's manganese. Magnesium right here. When it's reduced, it has a negative 2.37, but it's being oxidized in this example, so a positive 2.37. And the silver, that has a +1 charge, going to solid silver, means that it is gaining an electron. Again, make sure the charges add up on both sides. So when we come over to silver, and that's near the top, it has a positive 0.8 voltage. So very positive here. So we have a positive, what is that, 3.17 voltage. So yes, this reaction will take place. Okay. So again, when we're looking at these types of half reactions, one will always be oxidized. The other will always be reduced. You can't have 2 oxidation reactions in the same problem. You can't have 2 reduction reactions in the same problem. So one thing has to be oxidized, the other has to be reduced. All right, last example here, and then I'll let you start on your homework here. Example number 4. Calculate the standard free energy change for the reaction shown below. Now, what wasn't given on your equation sheet is this conversion here where we have 1 coulomb is equal to a joule per volt. You do have Faraday's constant, which is on your equation sheet, and that's in coulombs per mole of electrons. And we'll talk about that here very shortly. When we talk about calculating the standard free energy change, we're actually looking for delta G. So the equation that we'll use for a problem like this is the negative N, and then we'll have Faraday's constant, and then your voltage. Now again, if we have a positive voltage, that means that that negative here is going to cause the delta G to be negative. That's what we want. We want a positive voltage, so we have a negative delta G. All right, the number of electrons will always be a positive value. Faraday's constant will always be a positive. So the determining factor is my voltage. All right, so let's take a look at our reaction here, and let's find out what our voltage is. So iron, which is a metal or a solid, changes into iron plus 2. So how does that take place? Well, that is an oxidation reaction. So let's find out what that value is. Iron plus 2. Where are you, iron? Did I pass you? Sorry, guys, I can't find it. Here we go. So iron plus 2, and it has a, when it's reduced, it is a negative 0.44. In this example, it's oxidized, so it has a positive. Again, switch the sign if it's the equation spun around. So we have a positive voltage so far. Looking at our copper plus 2 and going to solid copper. Oops. So that means that it is gaining 2 electrons. And again, there's our copper plus 2. So copper plus 2 going to solid has a positive 0.34 voltage. So yes, we do have a positive voltage, which is very good. I believe that's a 0.78 voltage. All right, so now we can plug in our values here. How many total electrons? We're going to look at the end. How many total electrons are exchanged in this reaction? Well, the iron metal loses 2 electrons so that the copper ions can gain those 2 electrons. Since we don't have anything that we have to multiply by, let's just, for an example, say that this were a 3. Just for an example. Say that were a 3 and this were a 2. How many total electrons would need to be exchanged? Well, we'd have to multiply this top by 2 and this bottom by 3, which means that a total of 6 electrons would be exchanged. Well, in this example, there's only 2. So let's go right to it. So our delta G is equal to the negative number of electrons, so 2 moles of electrons. Faraday's constant, the F here, is somewhere, I can scroll down, there we go, is 96,500, and that's coulombs per mole of electrons. And again, a coulomb is a joule per volt, and it's per mole of electrons. Okay, and then our voltage, our E here, is that value there, so the positive, scoot down just a little more, positive 0.78 volts. And let's type all that in. So I know I'm going to get a negative value here. And I come up with 1.5 times 10 to the 5th. And what's my units here? Moles of electrons are gone. Volts are gone. Left with joules. Now, if the question was just asking for the value for delta G, we'd be done. Now, if we needed to convert that into kilojoules, make sure that we know that we are dividing by 1,000 joules to make 1 kilojoule. So if the question was asking for delta G in kilojoules, then it'd be negative 1.51 times 10 to the 2 kilojoules. All right, that should be enough to get you started on your homework.